Good afternoon, everyone. Welcome to Ooh, Shiny. My name is Jesse Barker, and this year I had the privilege of being chair of Real Time Live on Tuesday night and co-chair of Happy Hour. But here I'm just here to host this session of talks for you. The first one up, we have automatic Photo-from-Panorama for Google Maps. Speaking is Jared Johnson, who's a software engineer at Google working on imagery ranking. Jared?
Thank you. Like Jesse said, my name's Jared, and these are my collaborators on this project over the last couple of years. We encourage photography and recording. So in this talk, I want to show how we trained a convolution neural network from Street View panorama landmark detections and turn into a model that can automatically create representative regular photo reprojections from any spherical panorama. So a spherical panorama is a photograph of the sphere of all directions at a single point and single time. So 360 degrees along the azimuth angle, 180 degrees of elevation angle, so the whole sphere of directions. So in traditional photography, the photographer decides what's captured from any given vantage point. However, spherical panoramas capture everything, the whole sphere of directions. So this imagery has very high utility, as Google Street View has shown over a decade now. And viewing a spherical panorama can be very immersive. So it puts you in the same vantage point as a photographer. And I've been taking personal spherical panoramas for almost as long as Street View. And if I really want to remember what it was like to be at a given point and given time, I'll view these, and they give you the clearest, most uneditorialized picture of that place and time. So spherical panoramas are becoming ubiquitous. Street View is still driving around. We just announced a new camera last year. It's more detailed and better than our previous incarnations in every way. You can now take spherical panoramas with your phone, and it'll automatically do the stitching for you. And every year there's new, single shutter press 360 cameras that let you capture the whole sphere of directions instantly, either stills or video. And so taking these 360 panos has gone from this laborious stitching process that is often prone to error, to being able to automatically stitch one in your phone, to being able to do it with a single shutter press. So because of this, we've seen user uploads every day. The rate that people are putting this content on Google Maps has been increasing since 2012, when we allowed users to start uploading these photos and showing them on maps. And we expect this to continue. So this is Google Maps, if none of you have seen it before. And we're looking at Paris here, and we have the little imagery carousel open. And you can see a few spherical panorama thumbnails in here, intermixed with all of the other imagery pretty seamlessly. And these are representative, views of these panoramas, and they're pretty attractive, and it blends in well with everything else. And that's where we are right now, and I'm going to explain how we got there. So that's the problem the main problem that we are tackling here is, how do we generate the best small panorama thumbnail, given this spherical panorama that has all of the whole sphere captured. So this is the format of spherical panoramas that users upload, and it's called the equirectangular cylindrical projection. It's just a linear mapping of the azimuth angle to the x-axis and the elevation angle to the y-axis. So the main advantage of this projection is that the image along the horizon is fairly undistorted. So you can look at them and you can kind of tell what it is and where it is. So there's other cylindrical projections that have other advantageous properties, like preserving the area of things so that the poles aren't so blown out like this, but they usually come at the expense that like this distortion along the horizon. So this was kind of the best compromise that we can make for this kind of projection. Sometimes they're relatively interesting looking, and if we could just show thumbnail versions of these, then our job would be done. We wouldn't have to worry about doing anything. But as we can see, looking at these, there's a number of problems. So probably the most obvious distortion are how horizontal lines, as you move away from the horizon, get more and more distorted. This can kind of be disorienting. And then, like any other cylindrical projection, vertical lines are maintained, but if the camera is not actually upright when you're taking the picture, then the vertical things aren't actually vertical in the image. So even the horizon becomes distorted, and this just kind of ruins the panorama in this format. And then finally, back to the inherent distortion of this projection. The poles take up most of the image, and the horizon can often look kind of distant and small, and it makes it still difficult to see what's there. So any reprojection of a spherical panorama is going to have some distortion unless we only show some part of it. And we've actually done a study where we show users a representative part of the panorama versus these full equirectangular views, and they prefer the representative part 9:1 over the full equirectangular projections. So if we can find a representative view, then we can make our users happy and make better thumbnails. So can we agree? What's a representative view? Is it obvious? So I've kind of cut out the poles here to make this a one-dimensional problem of azimuth angle. If you were a photographer standing on top of St. Peter's Basilica, you would have the same question, which, if you can only take one photograph, which one do you take? And you probably take a picture of the square down below the basilica. If you did something else, maybe someone less familiar with Vatican City wouldn't even know where you were, but this probably gives you a high likelihood, and it's probably the most representative. So there's probably a right answer on that panorama. Even these more immersive panoramas where this is Machu Picchu and there's a beautiful view in every direction, but most the plurality of people viewing this would probably think this view is the most iconic of Machu Picchu and the most recognizable. So now that maybe you believe that there's often a best view for the panorama, how can we automate finding these? How do we automatically select a view that most humans would agree is representative? As I mentioned at the beginning of the talk, we're going to train a convolutional neural network, like so many other similar problems, image classification problems. So we looked at these tools of supervised learning, and probably the most obvious thing at the time was these convolutional neural networks were just passing human performance as they became more complex. In 2015 here, the winner of this image classification challenge passed human performance. So if we can frame this best view problem as a classification problem, then we can take advantage of these successes. So a kind of naive way maybe to do this is just the best view, saying that the best view or the most representative view is the same as the highest quality view. And maybe just train a quality classifier. There's a few problems that we foresaw here. So one is that every image in our corpus is technically a human chosen view, because every regular photograph, the human has looked around them and chosen which view to take a picture of. So this means that implicitly there might not even be any negative examples for this kind of classifier, in that, like, we want things that the human wouldn't point the camera at. Also, the dimensions of regular photographs that they differ qualitatively on, like color, contrast, texture, they might not be correlated with representativeness. Like, for example, these are two views from a single panorama, and you could argue which one was higher quality, but you probably couldn't argue that the left one was more representative than the right one. So, another natural transformation here then would be just take a panorama and have someone select a good view and select a bad view, and then train a classifier to tell the difference. So the problem here would be to train these convolutional neural networks, you often need like tens of thousands, if not hundreds of thousands of examples. So it would probably be costly to do this, and time-consuming to have humans go through panoramas and select views. So let me bring up landmarks here. So Google's landmark detection works not by just looking at like some external index of landmarks, but we actually have taken user regular photos and clustered them, and anything that, any large cluster that people have taken a lot of pictures of, we define as a landmark. So then when you use Google Lens and you take a picture of a landmark, or use Google Photos and you search for a landmark, the way we were able to identify those landmarks is because other people have taken a lot of pictures of them. And that's actually how we define landmarks. So, so one way to look at a landmark is, traditionally, what do people think are important? Another way is, like, what do people actually take a picture of when they're standing at a place? And that's kind of how we've defined them. So if we have enough panoramas that have landmarks in them, I'm sorry, for the spherical panoramas that do have a landmark in them, we would know with reasonable certainty where to point the camera. So that's what we did. We took our billions of Street View panoramas, and we ran this landmark detection on them, and we ended up with millions of landmark detections within these Street View panoramas. And judging from these kind of classification problems, this should be enough to train a good model. And this is what our training data looks like. This is just a sample of 6 pairs. We have the landmark detections on the right, and then we randomly point the view away from the landmark for the bad example. So for training, we're not reinventing the wheel. We just the current production model was actually trained on an internal GoogleNet Inception network a couple years ago. But we've recently trained a new model in TensorFlow using ResNet, a network that topology is included in this TensorFlow learning framework that's freely available online. This model has better performance than the old model, but we haven't done all the same evaluations, so the results that I'm going to go through now are going to be for the older model. And then for inference, we just take 120-degree field of view candidate reprojections every 45 degrees along the horizon, and the most likely good view according to our classifier is the one that we select. In production, there's this final cropping step that takes this wider field of view panorama and improves the composition in cases where it can by cropping the image, but describing this step is kind of outside the scope of this talk. I'm going to go through some results now to remind you. These are these equirectangular projection thumbnails of a variety of panoramas, and once we apply our trained model to these, we come up with these new thumbnails, which are all pretty representative and look good. Let me just do a side-by-side of half of them so you can see better. And here's the other half. So we also ran another evaluation on this model. We actually have about 12,000 human selected views from outdoor panoramas, and so we compared our model views to these, and so the difference. So over half of our model predictions differed by less than 56 degrees to the human chosen one. So if you're doing 120-degree reprojections, that means that the centers of each view are within the other view. So they're fairly close. We also asked human raters to decide on pairs of these projections, and we ran 3 separate studies. So it turns out that for majority panoramas, it doesn't, humans don't seem to have a preference on which way you point the camera, but for a non-trivial percentage, it doesn't really matter. And we didn't quite match human performance with this model, with the older inception network, but we definitely decreased the number of bad view thumbnails that we were generating. So as some final examples, I want to show you some of these improvements we effected. So before we even did this model, to make thumbnails, we would just use a heuristic that was kind of developed thinking about street view panoramas, where we would point the view at either the left or the right of the direction of travel of the camera. So for a street view panorama, this would mean that we're not pointing the view down the street. We would point it at the buildings on either side. But this kind of breaks down when you apply it to other kinds of panoramas that aren't on the street. So here we're in a cave, and we're kind of just pointed at the cave wall, and it's kind of, I mean, it's nice looking, but it's not as nice as what we get from the model, which is, we have the wall, we have the path we're walking down. It's much nicer and representative at the same time. And another example, this is a trekker pano, the backpack street view. And before, with our old heuristic, we were pointing at a bush, and then with the new model, we've improved it dramatically. Okay. So, any questions?
Yeah, really great work. But I'm wondering, so you mentioned non-level horizons. Did you have to correct for the horizons prior to making the thumbnails? How did that work?
That's right. So the Street View cameras and a lot of the handheld 360 cameras, they store their pose when they took the picture, so we can correct for that. But obviously, we can't just take the stored ones and make them smaller without doing that step. Yeah.
Another question.
Yeah.
Have you tried running this against panoramas of faces?
Panoramas of faces.
So my buddy's got a 360 camera. Pretty much the only thing he uses it for is when we go out for a team lunch. He can does that in the middle of the table and captures the whole crew.
Really?
I'm curious how this performs on that.
You'll probably find the most interesting person. I'm not sure. No, I haven't.
Okay.
We'll have to try that.
I'll send you just test image.
Okay, sounds good.
I have one.
Yes.
That's I guess it's more about the image format itself, like on disk.
Yeah.
Is it limited to the specific 180 to 180 ranges that you mentioned at the beginning, or would you be able to remap something to something like a cave if you wanted to be inside the panorama?
So you mean outside of a single viewpoint, like 3D data? So this is 360 by 180. It's the whole
okay. Sorry,
sphere
I misunderstood what you mentioned at the beginning. Then.
Oh, okay. Yeah.
And if there's no other questions, let's thank Jared.
Thank you.
Is his laptop set up? Oh, okay, great. Okay, cool. So next up, we have classified texture resizing for mobile devices. Presenting is Jae-ho Na. Jae-ho received his PhD degree from the Department of Computer Science, Yonsei University in 2012. Currently, he is a graphics professional at LG Electronics. He has co-authored more than 15 technical papers in the international journals and conferences, such as ACM TOG SIGGRAPH, IEEE TVCG, Computer Graphics Forum, and so on. His research interests include ray tracing, rendering algorithms, and graphics hardware. Jae-ho?
Hello, my name is Jeona. Hello, my name is Jeona. In this talk, I will introduce our recent work about classified texture resizing for mobile devices. My affiliation is Software Platform Lab in CTO Division at LG Electronics. If you are interested in this work, feel free to take photos. I will start my presentation with the introduction and related work session. For the last 10 years, graphics of mobile games have rapidly evolved. You can see the graphics difference between an old game, Angry Birds, and Black Desert. Like Black Desert, nowadays mobile AAA games exploit lots of high resolution textures for spectacular visuals such as shadows, lighting, and so on. However, use of many high quality textures increases the required power and memory bandwidth. It can cause low frame rates, overheating, or fast battery drains. To solve the problem, there have been some software approaches to control graphics quality. Two represented examples are Samsung Game Tuner and LG Game Battery Saver. These two apps provide a trade-off between quality, performance, and battery life by controlling resolution, frame rates of each app. But in contrast to LG Game Battery Saver, Samsung Game Tuner provides one more feature, texture quality control. In this talk, I will focus on this feature. This slide shows how to control texture quality by Game Tuner. The procedure has not been published in public, and this slide is based on our analysis on Game Tuner version 2.3. The procedure is as follows. First, each texture is rendered to an off-screen frame buffer. Next, the render results are read by a GL read pixel. Next, the texture is resized on a CPU. Finally, the resized textures is uploaded to the GPU memory again. This is a good approach to increase frame rate or decrease power consumption by resizing uncompressed textures. But there are some limitations. The first one is quality degradation. Resized uncompressed textures can bring out some visible blur effects. And each application range is also limited because compressed or dynamic textures are not resized. Also, each GPU, CPU, GPU processing can increase loading time increase. According to our experiments, it can increase loading time up to 2 seconds. Let me describe our approach from now. The goal of our classified texture resizing is to improve power efficiency of frame rates on texture-heavy games, but we wanted a better implementation than existing solutions. For our implementation, we consider the following things: how to minimize quality degradation after resizing textures, how to support various types of textures, and finally, how to minimize the loading time increase. How can we achieve that? Our answer is, after classifying textures, we can apply a different approach to each type at the OpenGL driver level. This slide shows our texture classification. We first divide textures to static and dynamic textures. Static textures are textures stored in an app, and dynamic textures are dynamically generated during each frame with render-to-texture techniques. Those static textures can be divided again to compressed and uncompressed textures. And compressed and uncompressed textures can be categorized again to multi-resolution min-max textures and single-resolution non-min-max textures. In the case of dynamic textures, we categorize the dynamic texture to shadow mass and non-shadow mass. If a shadow mass has the aspect ratio of 1:1, we regard the texture as a shadow map. Otherwise, the texture is regarded as a non-shadow map. This classification is possible by analyzing OpenGL commands. We modified the command dispatcher in the GPU driver to achieve our implementation goal. This slide shows an example of static texture classification in the game Beach Buggy Racing. Compressed min-max textures are the most widely used type for general textures, and min-max uncompressed textures are categorized for preserving fine details. Non-min-max uncompressed textures are usually one-to-one mapped to the screen. And finally, compressed non-min-max textures are usually used for sky and other environments. We apply a different approach to each type. For min-max textures, we simply control their min-max levels. And in the case of non-min-max uncompressed textures, we do not resize the textures to preserve fine details. And compressed non-min-max textures are re-encoded to resize the size of texture. The first case is ETC1 re-encoding for non-min-max compressed textures. We perform decoding, resizing, and re-encoding for these textures. And we need to minimize the encoding time rather than the decoding time because texture compression is much more complex than texture decoding. We only handle ETC1 and 2 formats because they are the standard formats in the OpenGL ES spec. For implementation, we use the ETC pack 0.5 library because this is the fastest ETC compression library with slightly lower quality than other encoders. For our implementation, we first ported the ETC spec code to the Mali GPU driver. We only used a single thread and we did not use SIMD optimizations. So currently our implementation is less optimized than the original ETC pack library. And additional ETC2 modules such as TH and planar modules are now applied to the to resize textures in order to reduce the encoding time. So in our implementation, an ETC2 RGB texture is re-encoded to an ETC1 texture. For min-mapped textures, we apply min-map level control. If a texture is judged as a min-map texture, the level 0 image is thrown out, and the other images are leveled down by one, as you can see here. The advantages of this approach are it is very simple and it has very low overhead. Also, it can be applied to both compressed and uncompressed textures, but there is one limitation. It is hard to detect whether a texture is min-mapped or not before loading its level 0 image, because the OpenGL spec allows a call over GL text parameter I both before and after a call over GL text image 2D. So currently we throw out the level 0 image of min-map after re-encoding, and it makes a loading time increase. We leave a solution of this limitation as future work. The third case is the no resizing for non-min-mapped uncompressed textures. This type of textures is usually one-to-one mapped to a screen, such as 2D menus, icons, and so on, and not compressed on purpose by graphics developers. Compression or resizing of this type of textures can decrease visibility, so we decide to not resize by CTR. Let's go to the dynamic texture classification. In the dynamic texture classification, we classify textures to non-shadow maps and shadow maps. And non-shadow maps include main frame buffer, G buffer, reflection map, velocity map, and so on. Note that we define the term the main frame buffer as a frame of object which has a different target resolution with the display resolution and is related to the frame buffer 0 at the end of the frame. The main frame buffer and G buffer should not be resized in order to prevent duplicated resolution or resizing. If we resize these two types, we will see the duplicated resolution resizing. So our choice is no resizing, non-shadow maps, and only shadow maps will be resized. This slide summarizes our shadow map resizing strategy. If the three conditions are fulfilled, we detect a texture map as a shadow map. First, the data pointer in GL text image 2D is null. Second, the width and height of a texture are the same. Finally, the text type is a depth image or depth data is attached using a random buffer object. The resizing factor of shadow maps is the same other types. And there are some cases when the resize cannot be applied. First, GL text storage 2D is used for shadow maps. It is hard to distinguish dynamics from static textures because we should additionally analyze GL text GL subtext image 2D functions. And if GL text images 3D is used for cascade shadow maps, our approach cannot resize them. And finally, in some cases, a shadow map has a different width and height. It is very rare but possible for higher quality shadow maps. Let's go to the result. We measure the power consumption of a GPU and DRAM. For our experimental environment, we used our own M8 keyboard with ARM CPU, ARM GPU, and LPDDR4 RAM. And we also use the National Instrument USB 6363 device to measure power consumption. For our experiment, we chose 3 Android games, Beach Buggy Racing, Implosion, and Genowar. According to our results, our approach can decrease the power consumption of GPU and DRAM up to 16%. This is the image comparison slide. This is the main menu of Beach Buggy Racing, and this is the original image. And this is the captured image with our CTR technique. You can see slightly less details on the leaf textures and flow textures. Back and forth. Can you distinguish them? Very similar. But in the case of Game Tuner, the leaf textures are similarly resized, but you can see visible blurring on settings and news icons. Also, compressed flow textures are not resized. This slide shows the loading time increase. As I mentioned, currently zero-level ETC RGB textures are re-encoded. So Beach Buggy Racing and Genowar show around 2 seconds loading time increases. It is comparable to Game Tuner, but it needs to be improved. In the case of Implosion, this game only includes ETC2 RGBA textures, so this game shows a slight increase within the error range, because only the memory level control without ETC1 recording is executed for static textures. So far, I've introduced our classified texture resizing technique, and as a future work, we'd like to minimize loading time increases by a clever mimetization technique and multi-threaded and CMD re-encoding implementations. Also, we are interested in extending our technique to wider format and APIs such as Vulkan, ASTC, and so on. Thank you, and any suggestions for collaboration with our lab is welcomed. Any questions?
Thanks. I have one real quick, if you don't mind, Jeho. Yeah. So I get everything that you've done. I'm wondering if are you suggesting that this is something you would do inside the driver on the device, or is this a recommendation that application developers would apply within their titles or whatever?
Application developers can naturally resize textures because it is very easy. But we wanted to implement this technique for all apps, all mobile apps. Even though I implemented this technique at the driver level, this technique can be implemented at the Android frame level. In that case, I think this technique can be applied to other GPUs such as Qualcomm Adreno or NVIDIA GPUs and so on.
Cool, thanks.
Good question. That was the question I was going to ask.
Oh, sorry. didn't mean to steal your thunder.
I have a question. You say that you dropped the level 0 and downscale the level 1 to 1/4. Why just don't drop the first 2 levels? Doesn't get the same result without recompression?
Yeah, the results. Okay. Yes, the results are the same, but this draw can make some loading time increase. So only 2 seconds loading time was increased, and the image quality is the same.
Okay.
Currently, we only analyze a single comment, but if we can analyze multiple comments by some comment queuing, I think this problem can be solved.
Well, thank you.
Thanks a lot.
Let's thank Jae-ho one more time. Cool. So next up, we have deep thoughts on deep image compression. Presenting is Rob Piquet. Rob is the head of new technology at MPC Film in London, now in his 12th year with the company. During his time there, he has written VFX software tools for a variety of films, including Harry Potter, Guardians of the Galaxy, The Jungle Book, and The Lion King. Most recently, Rob has embarked into more forward-looking research with his Shadow Lab compatriots, designing technology for the VFX studio of the future. Rob?
Okay. Thank you. Okay, just to kick things off, putting deep in your title twice is a really good way to get SIGGRAPH talks accepted. The reality is this has 0% deep learning in it. So if you're looking for a pee break, now's a wonderful chance. The other thing I'll say is I'm really here just on behalf of my team. Everything I'm going to talk about is really the hard work and coding of two guys back in London, Fabia and Apple. Thank you so much. Sorry you couldn't be here. I'm going to give a really quick refresher on deep images. This came out of a seminal paper from Pixar back in, I think it was 2000, and they were looking for a better way of doing shadow maps. And their kind of key breakthrough was to say that actually an image doesn't only have to have a single color or a single value per pixel, you could store an array of values per pixel. And in their case, and well, in our case as well, it represents different samples in depth. So effectively you're encoding X and Y in your image plane space, and you have multiple samples in Z or Z. So we'll take this kind of Vancouver house cat example here. This is what the 2D view of it would look like. But if we were to render this as a deep image, effectively what we would be capturing is all of the samples in depth that the camera saw. So this is basically kind of sort of like a point cloud representation of everything that the camera saw. When we do our path tracing, we'll typically send somewhere between 200 and 2,000 samples per pixel. So there's a lot of geometry that gets hit by one of those rays, particularly in like a furry creature setting. So that kind of leads into a little bit of a spoiler to, okay, what's the problem? So let's consider this example here, and I'll call this the grassy plain of doom. If we render this as a deep image, it's about 50 megs in size. And I should be honest and say that this is actually half res from our normal production settings. So I don't want to necessarily say that it would turn into 200 megs, but a full production resolution version of this grassy plain of doom would certainly be much more than 50 megabytes in size. By itself, 50 megabytes is semi-wrangleable. The problem is that we don't render still images. We are a visual effects company that produces shots for Hollywood feature film. So what that means is that we're rendering in stereo most of the time. Our average shot count is about 100 frames in length, and we are typically bidding on shows where it's 1,000 plus shots for a film. I tried to do some quick mental math and lost track of the zeros, but it's a lot of data. And the problem for us in particular is that we are very heavily invested in being a multi-site company. We very rarely process all of the data from beginning to end in one part of the world. We're routinely generating data in, say, Vancouver, and then need to process it in Bangalore, which is pretty far away, which means it takes a little while for all those little bits to get across the wire and through the ocean and however it works. I'm not a syncing guy. But this is kind of a pretty representative view of what our syncing guys go through when we tell them kind of what our data forecast is going to be, when we start to do that math and figure out how many zeros it's going to be. Okay, so back to the grassy plain of doom. Let's focus on this little pixel here outlined in white. And again, this is a deep pixel. It's not just a color. It is a series of colors in depth. In particular, it was 38 samples in depth. So what that means is actually this tiny little rectangle on screen here, there are 38, at least 38 different blades of grass that you can see through that little rectangle. And when you fire close to 2,000 rays, they will find them. And here they all are. So that seems like a lot, particularly if we consider this is a fairly background pixel. There's probably not going to be the predominant part of the shot. So what do we care about? Like out of these 38 samples, how many do we care about? And in particular, why do we care about them? The two main reasons that we render deep images at all is for content integration and for further image processing. So speaking about those very quickly, for content integration, our scenes are typically too heavy to render the entire thing in one go. We'll chop them up into different elements. So that was the grassy plain of doom. There's probably going to be some creature that's stomping through it. Maybe that creature is kicking up a dust cloud. Maybe there's another tree as well. And we'll render them all on different layers. And then we need to composite them together. And simple depth compositing doesn't work for us with anti-aliasing and edge issues and whatnot. We need kind of that deep, those deep files so we can kind of composite anywhere in there. And the second is image processing. We tend to do a lot of our depth of field as a post process. It's very expensive to do it in the render. And we find that our clients like to change their mind about what should and shouldn't be in focus very, very, very late in the day. And the idea of constantly going back to re-render just to change which blade of grass should or shouldn't be in focus is prohibitively expensive. So we allow them to delay their decision by pushing it further into the pipeline, pushing it down into a compositing decision. But again, to apply that effect in compositing, we need that rich 3D content in our 2D application. I guess you could argue Nuke is actually a 3D application in many ways now. So this problem is not entirely new. If we go back to the Deep Shadow Maps paper, they also realized that maybe there's more data that comes out of the renderer than you actually technically need. And they propose a whole section on how to do compression, how to effectively throw away samples. So we drew some inspiration from this. And if we look at the evolution of deep images from the original Deep Shadow Map paper to where we are now, where you can now represent colors and all kinds of stuff, one of the interesting additions in recent years is the notion of volumetric samples. So not only do you have kind of very discrete points as to something was hit at this specific depth, but basically you can specify ranges. So with a single sample, you can say that from here to here, transparency goes down by a certain amount. And it's well described in the OpenEXR literature how that math takes place. But out of the renderer, we're not getting that. We're only getting these very discrete point samples. So going back to this, we're only getting these 38 discrete samples as to where there were grass blades. And conceptually, we can probably think more about this as being a grass volume. We probably don't care about every single grass blade intersection, but we do care that until the first grass blade, we have full visibility. And behind the very last grass blade, we have no visibility. Everything's completely blocked off. But then between the two, there's kind of that slower fade, and we probably don't care about all 38 little events. So what can we group together? How do we decide what's meaningful or not? The spacing between these ones feels pretty close. I mean, we're talking about millimeters between grass blades here at a depth of, oh, I should say these units here are in decimeters, so this is like 5.5 meters out. We probably don't care about grass blades that are millimeters apart. But further out, the grass blades are further apart. Do we care about these distances? It starts to become a pretty subjective metric. Similarly here, and they're kind of spread in a way that is not immediately obvious. One of the things that we decided to think about a bit is that maybe this distance is actually not a kind of uniform thing. We shouldn't be just thinking about how far away are objects, but how far away are they relative to the camera. If I think about the audience members here in the front, if I put kind of just two fingers in front of each other, people in the front can probably say without a moment's hesitation, like, I can see which finger was in front of the other one. The people in the very, very back probably missed it. So our intuition is that we shouldn't think about depth linearly, but we should think about depth more logarithmically, and we should be adjusting our samples appropriately. And now at this point, kind of those front cluster grass blades and the back cluster grass blades, we can think that perceptually they have about the same amount of impact. So if we're going to cluster one, we can cluster the other. And that's what we go about doing. We kind of pick some threshold, some artist-defined threshold as to what is close enough, and we kind of say that in a perceptual way, like what's perceptually close enough. And then we just lump them together, and we convert all of those point samples into volumetric samples. So in this case, we went from 32 to 8, 38 to 8, something like that. And we reduced the image from 50 megs to 20 megs, which is still insanely large, but it's less than half. I mean, this is already a huge, huge, huge start. And if we bring this into Nuke for further processing, I mentioned that depth of field is one of the things that we like to do. So here's our depth of field running on the original image, Here it is running on the reduced image. And I'm pretty sure you can't tell the difference. I couldn't find a single pixel that was different. I tried to do a diff image and blow it up like 1,000 times just to demonstrate something. But it was really hard to see. And that suggests actually that probably we could have been even more aggressive. Changing the focus completely, so focusing on a different part of the image, again, in the original, the reduced. I mentioned we probably could have been more aggressive, so again, this is unlikely to be the dominant part of the shot, so we probably don't even need this many clusters. We probably could have gone down to this many clusters. Maybe we could have gone down to 1 even. But we allow this to be an artistically controlled metric, and it sits kind of pretty late in the pipeline, which is nice, because it allows us to experiment a little bit without any kind of costly re-rendering hit. So the next kind of thought we had is like, okay, there are different ways that we can think about depth and how important different samples are. So we talked about kind of a logarithmic manipulation of space. The next was to think about this depth of field post-processing and to imagine that samples that are in focus are probably pretty important, and samples that are super, super blurry, probably not so important. I wear glasses. Certainly if I was to take off my glasses and do this experiment, I definitely would not be able to tell you which finger was in front. So in this case, we're kind of focusing right on the mid-ground of this grassy plain of doom. And what we do then is we basically stretch space again. So we say that it's really important to maintain detail. We kind of apply this weighting so that wherever the in-focus part of your scene is, we say there's huge amounts of importance here, and as it gets blurrier and blurrier and blurrier, we say, probably less important. Which means that, again, kind of if we define a perceptual range for what we're willing to compress into a single sample, you can see that it has huge amounts of impact in the very blurry regions, kind of the very, very foreground and the very, very background. We can be incredibly aggressive in terms of what we compress. But in that in-focus region, we have to be very conservative and not blend together a whole bunch of grass blades where we might actually see that suddenly we're getting an incorrect result later on. So that's all about image processing. I mentioned that the other thing that we tend to do with deep images is object merging. So let's imagine that we've rendered 3 different elements independently. I apologize, that cat should have a transparent background. So we've rendered these 2 trees and this cat, and this is probably also not going to work with a transparent background. Oh, it does, good. And then we're going to slap them all together. And we're going to do some deep compositing to ensure that everything kind of nicely interleaves. So do we care about all of those deep samples? I mean, similar to the grassy plain of doom, these leaves, a lot of subpixel detail, there's going to be just loads and loads and loads of data, which is going to go back to our sad kitten face for our data wranglers. What we do is after those images have come out of the renderer, is we take the bounding box and we start to look for overlaps to identify kind of areas that we actually care about having detail in and areas that we don't. So there are kind of 3 patches right off the bat where there is no overlap between elements. And if we're not going to do any further depth-based compositing, like image processing for depth of field and things like that, we know that all of these samples are for naught. Like we just don't care. We're not going to use this stuff anymore. We can just flatten this. And finding these regions is super, super cheap. Like doing bounding box intersections is free. And then we can go and kind of compress all of those pixels, which is fantastic. Like huge savings right off the bat right there. Then we go back to the image and we look for areas where there is still some overlap. So in this case, we've got the mountain lion sitting on top of this background tree here. And we can go pixel by pixel, which is fairly quickly, and just look at where those samples are in depth. And we can look in particular for overlap. So again, it's a pretty cheap operation not to iterate over all the samples, but just to say what's the closest furthest sample for this element, say the mountain cat, and the furthest and closest sample for the background tree. And we can see that there's no overlap in these ranges here. So again, all of that detail is for naught. We don't care about it. So we can collapse all of that into, again, a single volume sample for this pixel. Where these 2 trees start to overlap, yeah, that's a problem. We do have to maintain that detail there. So we keep it. That's nice and simple. But it kind of outlines how very quickly and very cheaply we can identify regions where we can just start to throw away data very quickly and really, really bring down the file sizes. And we have to do this as a post-process. Everything I've presented here, it's not particularly academic. but it's kind of a practical kind of next step from what we get out of our rendering software. We don't write our own, we use commercial software for that. And ultimately, we know more than the renderer does. We're asking it to render a tree, then we're asking it to render another tree, and then we ask it to render a mountain lion. And at no point do we have the ability to tell the renderer, these are all going to be composited together in this certain way. But that doesn't mean that we have to accept that full hit of that enormous data set that the renderer gives us. We can compress it quite aggressively before actually passing it on to other artists to use, and of course before syncing it around the world. So this is actually in many ways just the start of some investigation. We're very curious to see what other metrics we could apply to these kind of compression algorithms, and mostly I hope to hear some thoughts from you. So thank you for your attention.
So you mentioned the ability for the artist to sort of have a certain amount of control over how, I don't know, how dense the area of depth is, I guess you might say.
Yeah.
What does that control look like? Do they give weights to certain ranges of distance, or how does that work?
Yeah, so in the submission for this, there's actually a little bit of math, which I chose to leave off the slides because I know it's the last day and everyone, including myself, is quite tired. We kind of tried to model a general formula that could be used to shape the space, which had about 4 parameters, kind of like an exponent and then kind of a scalar and an offset and things like that. And in observing the compositors working, we found that they were only ever playing with one of those 4. So we basically just dropped it all and just changed it to a multiplier. So like in the depth-based one, it's just a straight multiplier that you would say kind of at depth 1, I care about this level of detail, and it just kind of multiplies outwards. So depth 10, it's 10 times that threshold. We kept it super simple because I think 4 parameters was too much. They weren't using them and they got confused as to what they meant.
No, that's interesting. That was kind of what I was wondering about, if sort of giving them infinite control was maybe not, kind of not worth it.
Yeah, giving them 4 was 3 too many.
Okay. Any other questions? I didn't see anybody standing up, but want to give you the opportunity. Yeah, go ahead.
Just trying to understand the workflow. So as you said, this is a post-process. So really there is no disk space savage anywhere, right? No savings on disk space because like you are still keeping your depth images like with the information.
Correct. So there's no disk savings initially. The benefit is that we can start to treat those enormously heavy files, which previously would have ended up in our asset management system and synced around the world. We can treat those as temporary artifacts. And then do our compression, throw away that heavy mess, and now we've got something very lightweight that we can pass around and keep.
So just to be clear, this is kind of a pre-processing before the compositing?
Yeah.
Okay.
That's a perfect way to think about it.
Got it.
Hey, I was just curious, how heavy is that pre-processing? Like, is it quite CPU intensive to do that pre-processing, or how fast is it?
Yeah, I mean, it definitely maxes out the CPUs, but it's pretty fast. Well under a minute a frame, okay. Well under.
Well, you couldn't keep it as an interactive thing within the UI?
At full resolution, I think you'd be pushing your luck. It's at a minimum seconds per frame.
Do you give the control to, who sets the thresholds, the lighter, or do you give that control to the compositor if they choose?
So we give it to compositing, at least to set up, and then we try and find a ideally per show threshold that we want to use. Worst case per sequence is kind of our starting point. Ideally, people aren't touching it too much after that.
And the data that you throw away, do you have it so that it falls off, or do you just truncate it after a certain value?
In any of the any example in particular?
So say the area of overlap between the 2 trees is from here to here. Do you slowly fall off after that, or do you just truncate after the?
Yeah, so in this kind of example here, no, we just did hard cutting. I should mention this one actually rarely gets used in practice, despite the fact that it does have tremendous potential for throwing away data. People are always very nervous about the fact that it's like, actually, we might want to integrate another element that we didn't know about. And if you've just thrown away all the depth data, then you're kind of screwed. So yeah, while this one, in theory, has the most promise, it's the one we use the least often.
Hey, how do you make the artists care about applying the filters? Like, if it's an optional thing that they can apply, they might just not do it because they don't care about disk space, right?
Yes, so thankfully there is actually a side benefit to this, which is that a lot of Nuke's deep processing nodes slow down based on the number of deep samples that they're processing. So as the artists are compressing these things more and more and more and effectively reducing the number of deep samples in the image, their Nuke scripts start running faster and faster and faster. So it's actually in their best interest to get the best possible result out of this. Otherwise, yeah, it's tricky. Okay, thank you.
Let's thank Rob one more time. Thank you. Hi, just one quick thing that I totally forgot to mention earlier. If you go to the conference app on the page for this session, you'll see a session review kind of survey. It would be really great. We'd love to hear back from you about how you felt about the session in general, and you can give feedback and that sort of thing. So we would really love to hear that. So our final talk for this session is Synthesizing Panoramas for Non-Planar Displays, a Camera Array Workflow. Presenting is Isan Mandal, and he's the lead technical director at DreamWorks Animation's Themed Entertainment Group, which creates content for location-based entertainment and theme parks. He has been at DreamWorks for 9 years as senior technical director in various departments like FX, layout, and has credits in movies like Kung Fu Panda, Turbo, and Guardians. Previously, he was at the Walt Disney Animation Studio as a senior software engineer in the front-end tools team and has credits in movies like Bolt, Meet the Robinsons, and others. He holds a master's degree in visualization sciences from Texas A&M University. Isan?